Welcome back. In the last class, we were mainly focusing on the Monsanto acetic acid process of the carbonylation, and then we have seen the hydroformylation reaction. Now, in the today's class, we will just briefly discuss one of the asymmetric equivalent asymmetric case of the hydroformylation reaction, and then we will try to discuss the hydrocarboxylation, and if time permits, we will discuss the hydrocyanation reaction. Hydrocyanation reaction, by default, it's not really carbonylation reaction, but hydrocyanation is similar to that of the carbonylation mechanism. So we may want to put that in the similar bracket. Okay. So today again we'll mainly focus on one of the asymmetric case, and then hydrocarboxylation. Asymmetric hydroformylation is the one we'll discuss at the beginning. Okay. Asymmetric hydroformylation reaction are very important reaction, and again these are the reaction industrially done in a huge scale. Asymmetric hydroformylation reactions. One of the component could be, of course, if it is a linear product, as you know, as you have seen in the last class, there is no chance of getting any asymmetric one, right? Especially if it is a terminal olefin and linear one, we are not going to get it. But if it is a styrene one or a branch product formation is happening, then we can have this ligand which is chiral, and then we can have an opportunity to get the product in asymmetric fashion. Let's say for this case, with a suitable ligand, this gives the branch product, and EE is greater than 94%, and that means that of course 88:12 ratio of this product, right? 88:12 ratio for this linear is to branch product. Okay. Now for this particular case, that is very good, and we have 94% EE for these reactions, and we of course have the linear product a little bit. So from this styrene equivalent, we have two product formation, and that is the linear product, that is PHCH2CH2CHO, and the branch product. And if we are having a suitable ligand which is asymmetric in nature, which has suitable chirality, we be able to get the branch product in enantiomeric excess. That means in asymmetric version, and we are going to get for this particular case, let's say we get a more than 90% EE, which is considered to be very good, and nearly 95% EE, that's considered to, that is really very good. And then of course we have a linear is to branch product formation 12:88 ratio. That is again quite a good achievement. But one must notice why this branch product is all of a sudden is the major product. Why not the linear product is a major product? That's what we need to understand. One must understand that this is styrene, this is not propene or other aliphatic olefin, and therefore the answer lies within the nature of the olefin. Let me draw the metal alkyl species. So for the metal alkyl species, if it is a aliphatic one, this is the one which is going to be the more stable, and the primary one, and the secondary one is the one which will give you the branch product. Okay, it's going to be less stable. That's why for propene, for example, the one which we were discussing in the last class, this linear product is the major one, the branch product is the minor one. But for styrene, what is happening, that this is the metal alkyl, this is the least favored, and this branched one or the secondary alkyl species is more stable because of the charge distribution or the stability of the intermediate due to the resonance with the phenyl ring. Okay, negative charge is stabilized by phenyl ring, and that is how we have seen that this product formation is going on. Indeed, this is how the naproxen, which is the NSAID non-steroidal anti-inflammatory drug, which is used for pain and pain, fever, inflammation, and stiffness, or also for kidney stone, that naproxen, which is actually a very well sold drug, and it is synthesized by binap or tolulyl binap, or tolulyl binap, and this naproxen is synthesized in asymmetric fashion by utilizing this technique. Okay, so what we would like to take the message is very simply the asymmetric version of hydroformylation reactions are widely used in the industry. Specifically, a lot of drug molecules can be synthesized. One of the most important example, as we tried to say, is the naproxen synthesis, which has the naphthalene unit instead of the benzene ring. This is synthesized in large scale with binap or tolulyl binap as the ligand in industrial scale. And we know that this naproxen is one of the best selling perhaps drug in the world, and it is used for it is actually NSAID, so that means non-steroidal anti-inflammatory drug, and it is used quite large scale all over the world. Okay, so all these reactions, simple reactions, but can be utilized for humankind for industrial scale, and therefore we do want to understand the mechanism of it, and we have just seen that these mechanisms are very, very simple, and that is consisting of the fundamental steps that we have discussed so far in the class. In the next part, we would like to discuss the hydrocarboxylation reaction, the mechanism, and as you will see, this is again one of the simplest reaction and quite useful in industrial setup. Let's try to look back at that. Hydrocarboxylation reactions. Okay. Now, for this reaction, we again have an olefin, carbon monoxide, and alcohol. Okay, we have the same catalyst, cobalt catalyst tetracarbonyl, and we have the product formation where this is the RO equivalent, this is the RO, and then we have the CO, that is this CO. Okay, and then our olefin equivalent with two of the with the hydride in there, right? So we have RO, okay, from this alcohol, we have carbon monoxide from here, and we have our olefin equivalent from there. Okay, and now of course this reaction is going to be similar, as you can perhaps now draw the mechanism of it. Okay, I expect perhaps you should be able to do by now. It's a stepwise mechanism. If you try to draw, I think there's a good chance that you will be correct in predicting the mechanism. Let's try to draw the mechanism over here, and that will be the kind of the final mechanism for this course. And of course, perhaps we will not be able to discuss too much on the hydrocyanation reaction. The mechanism will be exactly similar to what we have seen so far. Let's try to focus on the hydrocarboxylation reactions. So we start with this CO3 equivalent. Of course, one of the CO unit will be lost. That's the first step, as you have seen in the last case. And starting from there, olefin will coordinate, and therefore you will have olefin coordinated cobalt intermediate. From there on, a beta migratory insertion will occur, and the carbon monoxide will also come in. We are kind of brushing in a little bit, and therefore we have after beta migratory insertion of this hydride into the olefin, you get the alkyl metal alkyl species, and of course also carbon monoxide get in. So 3 carbonyl become 4 carbonyl. From there on, alpha migratory insertion occurs to give you the intermediate, where one of these 4 carbonyl gets into the alkyl group migrates into one of these 4 carbonyl unit, and then you get this equivalent, which is ready for now the alcohol to give you the product. Okay, so alcohol comes in and you get this product formation. So this is the product, right? So again, once again, this is very, very simple. The mechanism wise, I guess the simplest hopefully by now to you. We have seen the metal carbonyl species, hydrido metal carbonyl species, losing one of the carbonyl first interacting with the olefin, and therefore beta migratory insertion and CO coordination gives you the metal alkyl intermediate. From there on, alpha migratory insertion, these steps are going to be repetitive, right? Exactly same thing we have seen before, the same thing is following, but only thing in the last step for the hydroformylation, you have seen the hydrogen gas coming into the picture. We have discussed that it is not, perhaps not the oxidative addition of the hydrogen gas, most likely it's a sigma bond metathesis. In this case, alcohol comes into the picture, and then from that acyl intermediate, we have alkyl carbonyl intermediate, we have attack by the alcohol to give you the product. Okay, we'll look at that last step once again, just like the hydroformylation case, we have looked at the hydrogen gas addition to the metal alkyl carbonyl intermediate. Here also we'll look at that alcohol intermediate, how this ROH is attacking on the metal carbonyl intermediate. Okay, alkyl carbonyl intermediate, which is bound with the metal. Okay, let's try to look at that. So the mechanism 1, first mechanism for that step, we need to draw the last step or last molecule what we were discussing. So this is the tris carbonyl cobalt intermediate with COR equivalent is there. If you have alcohol, of course alcohol can directly attack at this carbonyl center, gives rise to the intermediate where hydroxo from this one will be coming, and OR, it's a tetrahedral intermediate and from there on you have beta hydride elimination. This is alpha, this is beta, alpha beta, beta hydride elimination. So beta hydride elimination can give you CO3 equivalent along with the coordination of this COR OR equivalent, right? COR OR equivalent. From there you will get your product formation that you are looking for, OR and R, right? The release of this. So what you have seen so far is the alcohol is attacking at this carbonyl center, giving rise to the tetrahedral intermediate where you have alpha beta position hydride. This beta hydride elimination can give you the product formation along with the cobalt hydrido intermediate back to the method. Another mechanism would be mechanism 2, second mechanism, where you will generate upon attack by this equivalent by this alcohol, you will generate, just like SN2 reaction, you will generate ROH plus and OR, and this CO minus will be generated, right? So OR, and this carbanionic intermediate will be generated, and from there once again you will get the equivalent of this product formation where cobalt and the corresponding product is getting generated. So these are the two steps. Of course, another could be mechanism. There could be another mechanism where the methanol mechanism 3, where this alcohol will coordinate with the metal center. ROH will bind to the metal center and give you the corresponding product formation. So in the last step, what we have seen so far of these hydrocarboxylation reactions, there are 3 different possibilities. One, as the last one, the third mechanism could be ROH is binding with the metal center and then therefore attacking to this alkyl carbonyl equivalent. That's the third mechanism. The first mechanism we have seen that ROH is attacking on the carbonyl center and giving rise to the tetrahedral intermediate, from where beta hydride elimination is occurring to give you the product formation. The second mechanism, which is basically direct attack and in a concerted mechanism where you attack and release the metal equivalent from the intermediate, right? So all these 3 mechanisms are possible. It is it is still under debate which is the one that is exactly going on in these cases. Okay, so for the hydrocarboxylation reaction, we have seen a similar mechanism to that of the hydroformylation reaction. of course, both the hydroformylation and hydrocarboxylation reactions, we have seen that there is some ambiguity in the last step, which is of course one of the most crucial steps. We have discussed about the hydroformylation in the last class. In this class, we have seen the hydrocarboxylation reaction, and plausible 3 mechanisms are there. Of course, still it is kind of wide open which mechanism is predominant or which mechanism occurs in these cases. Now, of course, as you can understand, there would be an opportunity to do the hydrocarboxylation reaction in an asymmetric fashion, similar to that hydroformylation reaction. If you have styrene or let's say vinyl naphthalene or other aryl group as the part of the olefin or the vinyl benzene or vinyl aryl molecule, if you are having, then once again, similar to your hydroformylation reaction, you will get the branch product formation. And if you have the suitable ligand for the metal center, you can induce chirality into the molecule. So asymmetric version of this reaction can be developed by having suitable ligand. Okay. For the interest of time, we will briefly discuss again the hydrocyanation reaction. I think we can discuss for next 5-10 minutes or so. So the last topic of this course is the hydrocyanation reaction. Now, hydrocyanation reactions are the one where we will see into the olefin molecule, we will introduce a hydride and the cyano. Now, this, of course, this is not under the traditional banner of the carbonylation reaction, but the mechanism is going to be similar to that of the carbonylation reaction that we have seen, and therefore we would like to discuss this, and that will be the final topic of this course. Hydrocyanation reaction, similar to the hydroformylation reaction, you can have the linear version or the branch version. Linear product will be predominant, as you have seen for the aliphatic cases. If it is styrenyl cases, then you will have the branch product. Once you have the branch product as the major product, you may need or you may want to get the asymmetric version of this reaction, and that is controlled by the chiral ligand for the metal center. We'll see these are hydrocyanation reaction, particularly for one of the cases that we'll discuss over here. Okay. For hydrocyanation reaction, the general reaction type is the one over here. As you can see, if you have, let's say, if this is let's say naphthyl one or styrenyl one, we will get the nickel as the starting material in this case, and we can have the cord, as you know, cyclooctadiene can react with nickel with this nickel cord can react with the olefin to give you the corresponding R cyanos. In this case, asymmetric version we are talking about, and this methyl, and this when R can be of styrenyl, again naphthyl or styrenyl, we can get a good EE for this reaction. It's a chiral bidentate ligand we can use, for example, for this reaction. So the mechanism for this reaction will be, as you are trying to say, will be very similar to that of the reactions we have seen so far. Let's discuss the mechanism. So nickel will coordinate with the phosphine, okay, bidentate chiral phosphine ligand, let's say in this case, for asymmetric version, and olefin will come and interact with the nickel center to give you nickel olefin intermediate with the phosphine coordination. So of course, in order to generate this, you will have to lose the cord cyclooctadiene. Those are not that of a good ligand compared to the bidentate phosphine ligand. Therefore, the ligand displacement will occur to give you the so-called putative reactive intermediate, and then therefore we will interact further with the hydrocyanic acid HCN, and to give the nickel hydride and cyano equivalent along with the olefin coordination with it, and then of course the phosphine is coordinated. So what you have seen is the first of all, of course, ligand dissociation and phosphine coordination, cord dissociation and phosphine coordination, olefin interaction, so ligand association, exogenous ligand association, then HCN oxidative addition into the HCN to give you this this intermediate, which is pentacoordinated nickel intermediate. From here on, as you can see, the hydride is there, olefin is there. Of course, you can predict by now beta migratory insertion would be going on at this step. So beta migratory insertion will give rise to your the alkyl intermediate is the secondary alkyl, because the R group is styrenyl in nature or naphthyl, and therefore the negative charge over there can be stabilized. That's why we don't get the linear one, the branch one we are getting particularly in this case. From there on, reductive elimination will predominate or will pick up to give you the desired product of the hydrocyanation reaction. Okay, this hydrocyanation reaction, this hydride and the cyano is coming from here, and that is where we are talking about that this is a hydrocyanation reaction. Of course, hydrocyanation in industrial scale we can also use. These are the industrial scale reactions, sometimes utilized for the nylon preparation actually. So for example, butadiene can be reacted with hydrocyano HCN and to give you the adiponitrile dicyano intermediate. So two olefin attached with each other, 1,3-diene or butadiene. Now this butadiene can be converted by this hydrocyanation reaction to give you adiponitrile, and then that adiponitrile can be reduced to give you the diamine 1,2-diaminobutane basically, and that 1,2-diaminobutane can be reacted with the dicarboxylic acid to give you the nylon. So nylon 6,6 polymer amide can be synthesized by this process. So hydrocyano reaction, as you may know, is widely used in the industry specifically, let's say for nylon synthesis. It is quite popular. You can look it up. This is a very simple reaction where butadiene is reacting with HCN to give you the dicyanobutane, and from there the reduction of this will give you the 6 carbon containing amine, and that amine can be reacted with the dicarboxylic acid to give you the polymer, that is the polymer amide, also known as nylon 6,6. That is industrially used in a huge scale, and as you know, these hydrocyano reactions are little bit tricky to deal with. Care must be taken before handling, because you are going to deal with the HCN. So industry has to be extremely careful to utilize. So to speak, also the carbonylation reaction need to be dealt with very carefully, and proper safety precaution must be taken before doing these reactions. So what we have seen for the carbonylation and this hydrocyanation reaction, the reaction mechanisms are very, very simple. It's the ligand dissociation, ligand association, and then either your beta, then your oxidative addition, the beta migratory insertion, and some cases then followed by the alpha migratory insertion, and then reductive elimination or oxidative addition again for the hydrogen and so on, as you have seen. But the fundamental steps remain exactly same or similar. Either the sequence can change, but essentially you get the product formation very efficiently. Once again, this is the last class. I expect that you have understood the basics of organometallic chemistry, and specifically those reactions. You can study from any book. Some of these, of course, the ideas or some of the course organization. Of course, there was influence from my various teachers, but I hope I was able to give you an idea that these reactions are very, very efficient and can be utilized even in industrial scale. Of course, I thank all my teachers with whom I have the opportunity to interact, and they have influenced me greatly in teaching this course and organizing this course. I hope you have taken some message and you will be able to utilize these in your research or for further studies. With that hope, I would like to conclude this brief course, and would like to welcome for the future courses that I will be having on the organometallic and other related topics. Thank you very much for your kind attention, and please keep studying organometallic chemistry.